Well, good morning, class. So I want to do lecture on YouTube Live today, so that it's recorded, and because the goal today is to focus on reviewing for the exam that's this week. So I'll give you guys the exam on Thursday during the laboratory session. It'll be given to you via Sakai, and Brianna, I saw your name in the paper. It was the article about the arrest that was made last week. But I saw that I guess news people had interviewed you and asked you some questions. Anyway, so we're going to do a review for exam 1. It's this Thursday, and it's going to be given via Sakai. And I'll give you some more details on Wednesday about how this is going to happen. But I want you guys to be able to zoom in or connect to a Zoom session while you're taking the exam, so I can and do that on a mobile device or a second computer. So you can point that camera toward your work area, and I can proctor the exam that way. All right. Okay, so we're going to review descriptive statistics, and the tool we're going to use for descriptive statistics is Python in Jupyter Notebook. So let's do this. So I'm going to work through a review that's posted on my GitHub under Notebooks Reviews, Descriptive Stats Review. All right, so it's the material that we're going to go over is in this notebook, but I'm going to compose the notebook from scratch so you can really focus on what we're doing. All right, here we go. If you have any comments while I'm doing this, go ahead and put them up in the chat stream, and hopefully I'll see them. Okay. So this first exam is all about data, different types of data, different types of data scales, descriptive statistics, and hypothesis testing, but it's very narrow in scope. That is, the only hypothesis testing method that I want you to be familiar with for this first test is the z-test, okay? And okay, so let's start with, we talked about several different measures of central tendency. Please excuse my spelling errors. And this is, we talked about 3 specific measures of central tendency: the mean, median, and the mode. Okay, so let's do an example here. Let's just make up some data. And how would you find these measures of central tendency for the numbers 1, 3, 1, 2, and 4? You know, just made up data. And the answer is, well, if you're finding mean, you add those numbers together. You add these numbers together and you divide by how many data points you have: 1, 2, 3, 4, 5. Okay. For the median, you would sort them in order. So the mean would equal 1 plus 2 plus, 3 plus 1 plus 2 plus 4 divided by 5. And let's print that out there. Okay. The median, how would we find the median? Well, first you got to sort the data from in ascending order, which would be 1, 1, 2, 3, 4. And then what's the midpoint? And here it's an odd number of data points, so the midpoint is pretty easy to find. It's just 2. All right, now what about the mode? Well, the mode is the most frequent value in the data set, which in this case would be 1 because it happens twice, and all the other values just happen once. And so this is a simple example, and I will say this as clearly as I can. I will want you to be able to, if I give you a data set, just raw values, I will expect you to be able to calculate the mean, median, and mode of that data set. Okay, so that's coming. All right, now of course in Python, let's open this up. We can skip back and forth. Of course in Python, you don't actually do these things longhand. You're going to use built-in functions. So you can find the mean of a data set, the median of a data set, and the mode of a data set using built-in Python functions. The mean and median here are using functions that are built into NumPy or NumPy, and the mode is calculated using a function that's built into the stats package, which are imported here as tools. So while you'll never actually calculate mean, median, and mode longhand in practice, I will expect you to be able to do this on the exam. Do it once so you know what, that shows me that you know what they are. Okay. Next item, types of data or measurement scales, and there's four types of data, and they are nominal, ordinal, interval, and ratio. Taylor, I'll get to your question in a minute. Nominal, ordinal, interval, or ratio. Let's make this a little bigger. And I give you an example, 4 examples here, one for each type of data here, scale. So the masses of groundhogs trapped at Antietam National Battlefield during the summer of 2018. What kind of data is a mass? Well, masses are measured using instruments. Instruments have uniform scales of measurement. And in this case, the instrument has a natural 0 point. There's such a thing as zero mass. On the other hand, there's nothing to the left of that. There's no such thing as negative mass. So there's a well-defined 0 point when it comes to masses or weights. So what kind of data is that? That would be ratio data. The years various artifacts found in a Viking settlement in Newfoundland were created, determined through carbon dating. Okay, so years have an order. Okay, so that means it can't be nominal, must be ordinal, interval, or ratio. Years also have a uniform scale. Every interval of 1 year is the same. On the other hand, years don't have a natural, well-defined 0 point. Yes, there's year 0, but that's arbitrary on a scale. You can go back in time from that point. You can call that BC, and then you're counting the opposite direction. So years are do have a well-defined interval, but they don't have a well-defined 0 point. That would make year interval data scale. All right, next, the species of dragonflies caught near Rockcliffe Lake in Hardy County, West Virginia. So species are nominal data types. Okay. The ratings assigned to the quality of coffee beans sourced from organic growers, i.e. poor, good, and excellent. Now, you might think, well, this is the same. This is nominal data. These are just names assigned to coffee beans. But you gotta be careful because there is an order associated with these values that you would assign to coffee beans. Poor isn't as good as good, which isn't as good as excellent. So that makes these data values ordinal. There's a natural order in which they occur. Okay, so on the exam, I'm going to give you examples of data sets, just like I did here. And what I want you to be able to do is tell me what the data scale, the measurement scale of those hypothetical data sets are. Nominal, ordinal, interval, or ratio. Taylor asked a question about the format of the exam. And it's going to be given via Sakai, and there's no Jupyter notebook that you're going to be completing and submitting. It's all multiple choice, true, false, matching, and short answer, numerical type short answer questions. And it's all on Sakai. Okay. All right, next, variance and standard deviation. All right, so let's go back here to my my notebook where I'm building this stuff out from scratch, and let's take a look at deviation of calculating variance and standard deviation for an example data set. And let's use the same data that we had up here. So I'm going to create a list of these values in my data set. Okay. And did I get them all? 1, 3, 1, 2, 4. Okay. So the steps in calculating variance, and this is if you're not told otherwise, assume it's sample variance and then use the unbiased estimate for this. Okay, and so I will give you a small data set and expect you to be able to do this once so you can show me that you know where it arises from, out of what calculations it comes from. All right, so the first step in calculating the variance is to find the mean, which we already did. The second step is for each data point, find the deviation from the mean. Okay. The next step is to square these deviations and then add the squared deviations up. And then the final step is divide the sum by n minus 1, where n is the number of data points. Okay, so the mean we already found. The sample mean, called x bar, already found up here. It was 2.2. Okay. Find the deviation for the mean for each data point. Let me convert this data set into a NumPy array. Once I get all my pieces here, okay. So X is my data set. All right, so you would be able to calculate the mean by hand on the exam. I'm not going to give you a huge data sets. You know, I want you to be able to go through the steps of doing this for a small data set, understanding that the same process applies to large data sets, but you never actually calculate this by hand for large data sets. All right, so the next step, we found the mean. We added 1, 3, 1, 2, and 4 and divided by 5. The mean's 2.2. Find the deviation from the mean for each data point. All right, so this would be x minus x bar. I'm going to print it out here. So what is x minus x bar? It's taking each value in this data set and subtracting off 2.2. 1 minus 2.2 is negative 1.2. 3 minus 2.2 is 0.8, etc. Okay. What's the next step? Square these deviations. Okay. So in Python, squaring something uses the multiplication sign, but twice, like this, followed by 2. So that double multiplication means square what's in there. So I squared each of those deviations, and the first squared deviation is 1.4, etc. All right. And then the next part is to sum up those deviations. I get 6.8, or squared deviations get 6.8. And the last part is divide by the number of data points in my data set, which is 5 minus 1, which would be 4. Okay, so I get a variance of 1.7 for this sample. And that's the variance of x. And the standard deviation of x would then be the square root of the variance, which is 1.3. Okay, so back here, these steps are summarized again in the review. How would you find the variance and standard deviation of this data set? First, find the deviations of each value from the mean. Okay, then square these values and sum them up. Then divide by the number of elements in the data set, minus 1. And then take the square root to find the variance. All right, now of course, I want you to be able to do this once with a small data set, but then once you understand the mechanics of how it's done, you'll have a deeper insight into what it means. That's the idea. And then you will never have to do it by hand again. There's built-in functions in Python for calculating variance and standard deviation. You can even specify the degrees of freedom. So if you do DDOF equals 1, that does the sample variance, the unbiased estimate of the sample variance by dividing by n minus 1 instead of n. All right, but you see we get the same answers. All right, next up, visualizing data. How are histograms and bar plots similar and different? Know how to find the approximate location of the mean, median, and mode on a histogram. If the distribution is normal, then they will fall at the same location. If the distribution is skewed, they will not. If the distribution is skewed left, meaning it has a long tail toward lower values, then the mean will be smaller than the median, and the median will be smaller than the mode. Okay, what about box and whisker plots? Okay, so let's see here. Why don't we look at like an actual example on some images of actual examples here. So here, this is pretty good. All right, so in this picture here, it's showing two distributions which are not normally distributed. If you have a normal distribution, like this, well, that's not normal, but you have a symmetric distribution. The mean, median, and mode are going to be at the middle. So these three measures of central tendency will be exactly the same, and they'll be in the middle of the distribution. That's a result of symmetry. But if you have a distribution that's skewed, this type of distribution is called skewed right, or positive skew, which means it has a long tail in the positive direction. And this is skewed left because it has a long tail in the negative direction, or negative skew. All right, so what's the relationship between mean, median, and mode in distributions like this? Well, the mean is most sensitive to outliers. So these large values out here in the tail a distribution that's skewed right, or positive skew, is going to give you a mean that's higher because these values contribute to that mean. The median is less sensitive to outliers or long tails in one direction. So the median won't be as large as the mean, and the mode is, the mode is the most frequent value, but if you're thinking about binning values, the most frequent bin is going to be at the peak of the distribution in a histogram. Okay, so you should know these relationships between mean, median, and mode. Just qualitatively, not quantitatively, but if you see a distribution and it's skewed, you should know how that skew affects these measures of central tendency. Okay, so back here, let's take a look at some Python commands that I'd like you to be able to work with. All right, so I'm pulling in a data set. This is data set about serials. It's posted on my GitHub, and so I'm reading in a CSV file. In this case, there's a URL to this file because it's not on my local machine. All right, and I'm saving that data as my data frame. So my data frame, I could call this serial instead. It's just a name for my stored data. All right, so what does this command do? Serial.head shows me just the first couple rows of the data frame. So I think by default it just shows me 5, yes. But I can put in here, exactly how many rows I'd like to see, 7. So what I'm seeing here is a preview of the data, not all of the data. All right, I actually can't tell how many rows are in this data set by just previewing it here. All right, but it's a useful command because you can see the dimensions of your data set. Okay. Here's a very, very useful, and I changed my data frame name to serial, so I gotta change that here. But if I want to see how many, what's the size of my data frame, I'm going to use this command serial.shape. And so what the output you're getting here is the first number is the number of rows in my data frame. So that means in this data set there's 77 different kinds of serial. All right, 77 different kinds of serial in this data frame. And the 16 is the number of dimensions in the data. So there's 16 columns in this data frame. All right, so this is a very useful command, especially when you have huge data sets. You can't view them all at the same time. I mean, even if this was in Excel, you would only see a part of it at a time. You'd have to scroll down or scroll left, right to see it all. But you can see the shape of your data. You might say, well, what about size? Doesn't size just give me... Well, it gives me a number, 1232. What the heck is that? Well, it's 77 times 16. Oops, not plus. All right, so what is that? (77 times 16 is the number of data values in my entire data set. So it's the number of rows times the number of columns. So serial.shape is the one that's most useful. Serial.size will give you some information, but it's not in a useful format. All right, one more thing that at this point you should definitely know about working with data in Python is when you have a data, here I gotta change the name again. My data frame is, I called it up here serial, so I gotta make that change here. I want to extract a column from the data frame. One way you can do that is by referencing the column by its name. So if I want to extract the fiber column, the data in the fiber column, I can make a call to my data frame like this. Inside of brackets, I write in single quotes the name, and then I can view that data. Okay. There's other ways. Okay, so this is equivalent. In Python, most of the time, single quotes and double quotes are the same. So I could use double quotes and that works as well. So single quotes and double quotes work exactly the same. In this case, there is another shortcut, and this is because the column names are single words. So fiber is not like the fiber content. It's not multiple words, it's just one word. So another way that you can access individual rows in a situation like that is just the dot notation. I can put serial.fiber and it pulls out the fiber column. Okay, so all of these, here I'll write them all here. All of these commands do exactly the same thing. Those three commands do the same thing. They pull out the data in the column with the heading fiber. Okay. Let's get this right now. This is useful. Let's not skip it. This is useful too. What if you want to just know the rows where the fiber content is greater than 4? And one way you can do that is you can do a logical comparison here. And you can say, you know, where is this fiber data? Just pull that fiber data out of my data frame, greater than 4. And the results that you get are just trues or falses. So what does this mean? This means that in row 0, let's go back up here. In row 0, fiber content is 10. In row 1, it's 2. These are grams. 9, 14, 1, 1.5, 1, 2, 4, and 5. So what you're getting here is a true if the fiber value is greater than 4, and you're getting false if it's less than or equal to 4. So this is very useful at times to be able to figure out which data values are larger than some or smaller than some threshold value. And if you wanted to just pull those values then out of your data frame, you could pass that list of trues and falses to your data frame, and what you get is the high fiber results. So row 0, row 2, row 3, row 9, row 27, 24, 52, and 58 are the high value, high fiber serials. So you can isolate data by using references like that. All right, I won't ask you a question about those techniques on the exam though. On the other hand, there will be a question about, several questions about hypothesis testing, z-scores and hypothesis testing. All right, let's spend some time here. So let's use this data set here and try to answer this question. Let's try to answer the following question. Is the mean rating of Nabisco cereals, we'll call that the sample mean here, X bar, different than the mean overall rating of all cereals in the population mean? Okay, so here we only have 77 cereals, but we're going to call that 77 cereals the population for the purposes of this example. Obviously, if you've been to grocery store recently, you know there's more than 77 different kinds of cereal. All right, but we're going to say that these are the population. All right, so we formulated a null hypothesis. The question we're really interested in is, are Nabisco cereals rated differently than the other cereals? So the null hypothesis would be there is no difference. that the population mean mu is equal to the sample mean x bar. And the alternative then would be that there is a difference between those two. So we're going to use the alpha equals 0.5 significance level, and we'll use a z-table to look up the critical value. Now, one thing here is a question that you need to answer before you proceed is this a one-tailed or a two-tailed condition on this example? And what's that mean? Well, we are going to be using probability distributions, and in the case of the z-test, the assumption, which we've skipped over here, is that the data is normally distributed. Okay, so we're gonna just assume that our serial data overall rating scores are normally distributed for the purposes of this example. All right, and then you have a probability distributions, and the normal distribution has two tails. It's like, it's got a tail to the left and a tail to the right. And if you're looking to see if a value overlaps with that distribution or not, all right, the question is something is equal to something else. There's significant overlap in the sample distribution and the population distribution. And the alternative is they don't overlap. There's no direction associated with that alternative. You don't care if the sample is greater than the population or the sample mean is less than the population mean. You don't care about that. There's no inherent, and that's how it's stated here. There is no difference, or there is a difference, but you don't care about the direction of that difference. That makes this a two-tailed condition. Both tails of the normal distribution matter in this case. Now, if this was restated and that the alternative was that Nabisco serials are better than all the rest of serials, then there's a direction, and then that's a one-tailed case. Okay. All right. So we're going to use a two-tailed case, and let's look at a z-table here. Oh, this is all right. Z-table here. You'll be able to pull a value out of here on the exam, and first you have to determine, is it a one-tailed or a two-tailed case? And the numbers on the table are probabilities of different z-scores. And for the two-tailed case, and these are positive z-scores. So these numbers, I wish there was a picture. Let's find a different one. Let's try this. All right, let's use this one right here. So the numbers here are the probabilities, the areas under the curve to the right, the left of each of these z-scores. So if you have a two-tailed case, you got to take these probabilities that are on this chart and double them. All right. So if we're after the alpha equals 0.05% significance level, the value we're actually looking for on this chart is not 0.05 but 0.025, because it would be doubled in the case where you have two tails. All right. So where is it? It's right here. 0.025, and then the z-score that goes along with that is negative 1.9, and then we'll go up to find the next decimal point, 6. All right, so the critical value is negative 1.96, or, because we don't care about direction, positive 1.96. Okay, so there's actually two critical values that would have us reject the null hypothesis. If you have a number that's less than negative 1.96 or a z-score that's greater than positive 1.96. Both of those situations are sufficiently far away from the population mean to yield significance. All right. So I'm going through the process here of actually calculating some stuff And let's see if this cell runs for me. Yes. So what I've calculated here, and I've used these names to communicate what's going on. Mu is this is the mean score of all the cereals in the population, which, again, is not actually the population of cereals, but it's our population, 77 cereals. So this is the mean score of all the cereals. And this is the standard deviation. All right, so the population statistics are required in order to do a z-test. All right, what about the sample? So this is x bar. This is the mean of score of the Nabisco cereals only. So it looks like, just on the face of it here, Nabisco cereals have a higher average score than everything. Okay, what's our sample size? Well, there's only 6 Nabisco cereals in our data set. Okay, so how do you go about, let's go over here to a blank screen, and let's summarize how you go about, how is a z statistic calculated? Okay. All right, so the first thing to do is let's talk about what you need in order to calculate this. Okay, so what you need is you need the population statistics. Okay, mean and standard deviation. Okay, typically those would be given to you, okay, or they'd be knowns. The population stats, mean and standard deviation. All right, so these are abbreviated with the Greek letter mu and the Greek letter sigma. Okay. What else do you need? Well, you're also going to need to know the sample mean, which uses the symbol x bar. So you're going to need to know those two things. You also need to know the sample size, call that n, little n. And then the last thing you need to be able to do is calculate, or let's say estimate the standard error of the sample mean. Okay, actually, let's erase that because that's not what you need to know. That's a step. Okay, so now let's go down here to what you do. Okay, so the first thing you're going to do is find the difference between the sample mean and the population mean. Okay, so that is x bar minus mu. All right, the sample mean minus the population mean. So this is a measure of deviation. I don't know if I can do, nope, that doesn't work. All right, the next thing you need to do is you need to calculate the standard error of the sample mean. How do you do that? Standard error is equal to the standard deviation of the population, sigma, divided by the square root of n. All right, so it's the standard deviation from the population divided by the sample size, square root of the sample size. So the standard error of the sample mean gets smaller as your sample size increases. All right, and then the last thing is find the ratio of these two things. Deviation over standard error. All right, so that is Z is equal to the deviation between the sample mean and the population mean divided by the standard error of that population mean. Okay, so in practice, will you ever actually calculate a Z statistic? Well, you will when you take the exam. You'll have to calculate this once, and then after that, well, if you ever do a Z test, which you probably won't, because of the underlying assumptions, you could use a built-in Python function. So if you're not going to use, the reason you would never actually probably calculate a Z statistic is your sample size is too small. And when you have small sample sizes, you can't really estimate sigma for the population very well. So when you use the sample standard deviation as your estimate for sigma, the standard deviation of the population, you're going to end up having longer tails in your distribution than you would in a normal distribution. And those longer tail distributions are called t-distributions. So you never actually do z-tests on experimental data. You do t-tests. So why are we learning about z-tests? Because it's laying down a foundation for how hypothesis testing works. And it's also sort of prototyping this idea of calculating these inferential statistics that you do in z-tests and other things. And these statistics are in many situations of a form that are the ratio between a deviation in the numerator, some measure of deviation between your samples or your sample and something else, divided by a measure of variability in your sample or samples. So it's always a ratio like this, measure of deviation divided by measure of variability. Okay. All right, so let's go back here and let's look at the results for this data set for the serial, the Nabisco serial. So our population statistics are here. Here's our sample mean, our sample size. So I calculated the standard error of this mean. Here it is. The standard error is the population variance, sigma, divided by the square root of the sample size. Okay. And that standard error is 5.69. And then I calculate the z statistic, which is the deviation between the sample mean and the population mean divided by standard error. And I printed that out. Okay. So my z statistic is 4.44. Is that bigger than my critical value? Yes, much bigger. The critical value was plus or minus 1.96 for this test. And our z-stat is much bigger than that. So that means it's very, very unlikely, much, much less than 5% likely, that we would get this sample mean from a random sample of cereals from the population. All right, it's very unlikely that this difference that we're seeing between 67.968 and 42.665 is just due to random chance. It's very unlikely it's just due to random chance. So therefore, we reject the null hypothesis and accept the alternative, that this difference we're seeing is real. All right, so we reject the null that Nabisco cereals are as good as all the rest and accept the alternative. Moreover, we can add a little bit of interpretation. Our z-score is positive, so that means that Nabisco cereals are not only different than the population when it comes to quality score, they're better than the population. All right. Okay, let's see. One more thing here. Box plot. So I'm making a box plot here, also called a box and whisker plot, and you should know what you're looking at here. There's actually two data sets posted here, but this is a great way to summarize your data and to show differences between data sets. So this is the ratings of all the cereals in the data set, and this is the ratings of Nabisco cereals. Okay, so you see the distribution in the box and whisker plot of scores of all serials is over a wider range and centered at a smaller value than the Nabisco data set. So when you're looking at a box and whisker plot, what you're actually looking at here is this central box right here is a box that encapsulates the middle 50% of your data. So 50%, if you go down here to the x-axis, we can't read this exactly, but this is about a score of like 33 and this is like 53. So when you're looking at all the serial in the population, 50% of the serials have a rating that's between 33 and 53. All right. This line then, if this is the 50% of the data, this line represents the first quartile. 25% of the serials have ratings that are less than this value. And that makes this the third quartile, which means 75% of the data have ratings less than this value, 53. And the orange bar in the middle is the second quartile, which means 50% of the serials have ratings less than this value, around 40. Another name for the second quartile is the median. It's the median. So the orange line represents the median. 50% of the data is to the left and 50% is to the right of that value. So first quartile, median, third quartile. All right, now what about the whiskers? So that's the box. Oh, and this this middle 50% of the data, it's also referred to as the interquartile range. The interquartile range here is about 33 to 53. It's the distance from the first quartile to the third. All right, so that's what the box represents. What about the whiskers? There's one to the left and one to the right. Well, the whiskers show the range of values, and the extent of the whisker is going to show the minimum value in your data set and the maximum value of your data set. Minimum value, maximum value. Except there's this circle out here. What is that? That represents an outlier. There's a serial in our data set that's way out here above 90 in the ratings. And that makes it an outlier. Well, why is it defined as an outlier here? Well, you could turn that functionality off, but what's happening here is the whiskers extend out as far as the maximum and minimum values unless the maximum and minimum value is greater than 1.5 times the interquartile range higher than this box right here. So this value is, in other words, in this case, the interquartile range is this distance right here, and the distance of the length of this whisker is 1.5 times that distance. So this value is beyond that distance, so it's considered an outlier and it's labeled with a circle. All right, so that's it for the review. If you can master all of those things that we talked about today, you will do excellent on the exam, which I'm giving to you on Thursday during the lab session. Okay? So this video review will be, I'm going to archive it on my playlist on my channel on YouTube, so you can come back and you can watch it 100 times if you want to. But who would want to do that? All right. So that's it for today. I will see you on Wednesday. Have a great rest of your day. Bye-bye.